Welcome to the workshop. We want to continue taking a look at the third section of the appendix. We've already taken a look at several examples of direct proofs, two relatively basic examples, and then an example that required cases. Here what we want to do is we want to look at a slight variation of a direct proof. And it's maybe, well, yeah, essentially that's what we're looking at here. So we talked about in the section regarding logical equivalence, we considered a couple of statements. So an implication we found there is equivalent to its contrapositive. So sometimes an implication might be difficult to show, but the contrapositive might be much easier. So what we can do is, if we know that the contrapositive is true, we in fact know that the original implication is true. So we flip it using the contrapositive, prove the contrapositive, and then again use the contrapositive to flip it back to the original statement to be able to conclude that the original implication is true. So that's the idea of a proof by contraposition. Let's take a really quick look at our notes. Let's see. So this gives an outline here of what a proof by contraposition should look like. Again, we're trying to prove P implies Q and an implication. So what we want to do is we want to recognize that P implies Q and not Q implies not P are logically equivalent. So if I'm capable of proving this, then by logical equivalence, I have proven that. And that's what we want to make use of. So when we write a proof by contraposition, we assume not Q, because what we're doing is we're proving not Q implies not P. So we assume the premise of the contraposition, which would be not Q, so assume not Q. Use our definitions, our theorems, our well-known knowledge, our well-known facts. Okay, we use these things to manipulate and find that not P is true. So we have that the implication not Q implies not P is true. Once we have that, then we can go ahead and say by the contrapositive of this thing, right? Because the contrapositive of the contrapositive gives us back the original statement, right? The contrapositive of this would be not P implies not Q, but that's the same thing as P implies Q. Okay, the original implication. So when we take the contrapositive of this, we get the original implication, and we are happy as can be. So again, that's the idea. That's the format of a proof by contraposition. So for this example, what we want to do is we want to consider two integers m and n, and this looks really similar to our previous example. So if 3m plus n is even, then m and n are of the same parity. You'll notice that that's, I believe, the inverse of the statement that we proved last time. So ignoring that little bit of information, we want to prove that if 3m plus n is even, then m and n are of the same parity. Now you might start off with some side work, right? You might not know where to start, and that's okay. You might not know where to have started for these other proofs that we've already done as well, and that's okay, right? If you want to write down some scratch work, there's zero problem with that. Now, do you have to include that in your final solution? No, not at all. But you might start off with some side work. So if I wanted to assume that 3m plus n is even, that would allow me to write 3m plus n is equal to 2 times k for some integer k. But then what I want to do is I want to show that m and n are of the same parity. Now, if I have m and n are of the same parity, then of course I know that 3m plus n is even, but that is not how it works. We can't say, let's assume that this is even, and then when they're the same parity, it's true. No, what you've just done is you've assumed the premise is true, and then assumed the conclusion is true, and showed that the premise is true when the conclusion is true. But that's not what we're doing, right? When we want to have a direct proof, we want to show that when the premise is true, the conclusion is true. So if we wanted to take a direct proof approach to this theorem, we would have to start with this and then show that m and n are of the same parity. How could we do that? Well, you might solve for m and say m is equal to 2k minus n, but I had to divide by 3, so it's 1/3 of that. So can I write m as an even number easily or m as an odd number easily? No, not when I have this. Or what if I know something about n? If I know that's even, then I have a factor of 2 that I can pull out, and it's 2 times 1/3 of something. But how do I know that that is an integer? 1/3, right? 1/3 of 2 is not an integer, not equal to an integer. So having this fraction there is a big problem. You might be saying to yourself, well, Dr. Reinhardt, couldn't you write it as n is equal to 2k minus 3m? 2k minus 3m. And then when we know something about n, that actually tells us quite a bit about n. Yeah, you're right, you caught me. But the problem is that we won't be able to take every problem, approach every problem in this way. For example, if we had 3m plus 5n, then we would still have 5n is equal to 2k minus 3m. And it actually works out that even if we changed it to 5n here, the statement overall would still be true, or the implication would be. So if I needed that, then n would be 1/5 of 2k minus 3m, and that'd be the same in the same boat as I was here, right? I don't know that that 1/3 times something is still an integer. So there's a little bit too much unknown here for us to be able to quickly and easily go through showing that 3n plus n is even gives us that m and n are of the same parity. So what can we do? Well, what we can do is essentially turn this into the same problem that we looked at last time. And what we looked at last time was that if m and n are of the same parity, then 3m plus n is even. And we're going to flip it though, right? Because we're going to switch the order and negate. So if m and n are not of the same parity, then 3m plus n is not even. In particular, it is odd. Okay, so we can take the contrapositive and prove that. And that is pretty easy to do, because if we know a relationship of m and n and we have a representation for m and n, then we can consider all cases, write them out, and then find what 3m plus n is and draw our conclusions there. We could take our smaller pieces of information and bring them together. That's easy to do. Taking our one piece of information, 3m plus n is even, and splitting that up into two pieces of information about m and n, that's a bit more difficult. So we want to use the contrapositive to show this. But I want to take a brief pause, go ahead and stop the video and actually look at this proof in our next video. So I'll see you guys back in the workshop very shortly.